All right, so chapter 6, we're going to start talking about some of the hardware that you actually use in a network, and we'll talk about switching and routing. And we've talked a little bit about switching before. I've mentioned that switches are better than hubs, and the reason for that being because they create individual collision domains. So we're going to talk about LAN hardware. We'll talk about some of the things like a network interface card. There's another acronym you need to know because they're going to use that all through the test, NICs. Hubs, bridges, switches, routers, and gateways. And we'll also talk a little bit about VLANs, which that's a virtual local area network. I'll explain what that is to you. And then we'll talk about IP4 and IP6. So your NIC is the device that actually connects to the media, or in the case of wireless, connects to the antenna. It is a transceiver, which means it transmits and receives data. It falls in the physical and the data link layer. And the reason it falls in both, it falls in physical because it's actually transmitting data, but it falls in the data link layer because the NIC is where the MAC address comes from, or the hardware address that you've got on every device. So some NICs, especially those that you use in servers, might do some things like prioritization. They offer network management, buffering, and some have traffic filtering. Now, do y'all all understand what a buffer is? All right, a buffer basically is just memory that's on the network card. And if data comes in off the network too fast for the device to process, it goes into that buffer until the device can process it. And with slower networks like 10 and 100, that's not a big deal. The buffer's hardly ever used. But you get up into some of these super high-speed networks like 10 gigabit fiber, they need a big buffer because sometimes the network's actually faster than what the computer can process. So the buffer takes care of that for you. The NICs don't analyze any of the information, though. That's all done in layers 3 through 7. All the NIC really does is takes that data, packages up, and transports it. So before you install a NIC, you need to know the interface type. Usually network interface cards only come with one type of media that they'll take, like the ones in here are all twisted pair. If we were running fiber in here, we'd need fiber media cards for all of these. So you got to make sure you get the right one for what you need. And NICs are dependent on several different things. The access method, which is, what we're talking about, the cable or whatever. The type of connector interface, the speed, it's got to be compatible with the motherboard. If you've got a motherboard that only has PCI Express slot and your NIC is PCI, it's not going to work. And then some have advanced features. And that gets more into the line of like server network cards. One thing that is becoming popular on network cards in security, for example, is what they call cryptographic offloading. And what that means is that the NIC itself has got a little processor on it, and it does the encryption of data before it's sent out on the network. So that makes the whole computer faster because the processor in the computer is not spending time doing the encryption. You've actually got the network card doing it for you. So you've also got to know the bus, and that's the circuit signaling pathway. That's what I'm talking about when I say PCI or PCI Express or USB even as a type of bus. They differ according to capacity, and the data path size is the number of bits that can be transferred at any single time. You won't really need to know this so much for NetPlus, but the fastest right now is the PCI Express slot. And then PCI probably is right behind that, and then USB behind that. But USB, you see a lot of USB network cards because it's very convenient. You don't have to even open up a machine to plug a USB network card into it. You just stick it in the side. So the expansion slots are in the motherboard where the cards actually go. Those cards are called expansion boards. A NIC is sort of an expansion board if you get one to add to your computer. Now remember I told y'all that most computers now, almost any that you buy, are going to have a network card built onto the motherboard. And that's just because it's convenient. I think all of the ones in here have got, every computer in this room has got the NIC built into the motherboard. So if you look at the ones like behind you, you'll see that it's not actually a card that it's in. It's actually just part of the motherboard.
But it will eventually fail.
It could eventually fail, and that would be one reason that you would add one to it, is if the one on board fails, you could add one. This gateway up here, I think it may not have one on board. Maybe added it. Nope, it's on board in that one too. But these are the expansion slots we're talking about. You see, this one had 2 cards in it that somebody removed. You could put a network card in there. And the reason you would do that mainly is exactly that. Your network card failed and you needed to add one, or you need some different type of media, or you made it a server and you want something special. The network cards that are built into these are kind of generic. So if I wanted, and like these are probably all 10100, so if we wanted to do gigabit network, you maybe would add a card for that. Or if we had fiber, you'd have to add a card to get on the fiber network. So here are the different types of addresses. PCI is a 32-bit bus. It was introduced in 2004, 1 gigahertz speed. To determine what bus you need, you can either read the documentation or look inside the case. So USB NICs, they call that a peripheral NIC, and that's attached externally. And there can be all of these others. I just finished a A+ class, and in it I talk about all the different types of external connections. But basically, USB is ruling the world now when it comes to external devices. You can get a FireWire network card, but that's really only going to be seen on a Mac, and they're not very common. PCMCIA is an older thing that you could add to the side of a laptop that was actually a little card, and those have pretty much disappeared. So has Compact Flash, because USB with USB 2.0 is just as fast as any of those. And now that USB 3 is coming out, it's going to be even faster. So be aware that those exist, but for the most part, know that if you're going to put something external, if you're going to put like a network card on a laptop, 9 times out of 10, if not more, you're going to end up doing USB. Here they're showing an example of a USB NIC. From looking at it, we can tell that's a wireless one because there's nowhere to plug the wire into it. It's a very generic looking one at that. So on board we talked about is connecting directly to the motherboard. Almost all computers and laptops now, if you bought one in the last 5 years, chances are very high it's going to be built on. And the reason that saves space and it frees the expansion slots for other things. And here they're showing just a motherboard. If you look, that motherboard's got 2 network cards built onto it, and they're right here, right here above the USB slot. Something I learned from the A+ class, just random, but good information to know. If you think your machine's got USB 3, or if you don't know if a port's a USB 3 port, the way you can tell is that blue. See, this computer's got 8 USBs, or 10 USBs across there. No, 8. 2, 4, 6, 8, 10. I was right. But those blue ones are USB 3. USB 3. Yeah. And that will be on your test, but that's something that I just learned. I didn't know that either, so I thought I'd share it with you. All right, so installing a NIC, read the manufacturer's documentation, gather what tools you need. You're going to need probably a screwdriver. Unplug the computer. If there was a network cable in it and you're replacing a NIC, unplug that. Ground yourself. It is important when you do anything inside the computer, either put on a wrist strap or my favorite is just touch the side of the case with it still plugged in. That'll ground you out so that you don't shock yourself or anybody else. Open it up, take the bracket, push it down in it. When you're putting a network card in, you've got to be a little forceful, but don't push too hard. You'll break the little contacts on it if you do. And then put the cover back on, turn it on. And in most cases, if it's plug and play, you're done. Windows will then boot up and find the driver and load it, but if it won't, then you'll need to configure the driver. Here they're showing just an example. That's a 3COM card stuck in a PCI slot on a computer. That actual network series there, that's a 905TX. That's a very popular card back in the days before there were built-on network cards. Some of the servers back there that we've got a second network card in, that's the card that's in them. And at one time they were expensive, but now network cards are 15, 20 bucks a piece. They're cheap these days, especially for just standard networking. You get into expense with fiber cards, but not so much for these. Okay, so the driver is the software that enables the device to communicate with the operating system. And if you purchase the computer with the peripheral, the drivers may be installed, but if you add it, you may need to install the drivers. Again, with Windows, it may try to detect it and load them for you. Network cards are one of those weird things, though, that if Windows doesn't have the driver, you're going to need a disk. And the reason's obvious if you think about it, but most people forget. When you plug in a device like a mouse or something, Windows can go out on the internet and get the drivers for it. Well, if your computer has the network cards died in it and you put in a new network card, you don't have an internet connection most likely, so it can't go out and find the drivers. This is why one thing that I keep in my toolkit at all times is a little USB key, because inevitably I will help somebody, I'll rebuild their machine, and I won't have drivers for their network card. And there's no way to get them on their computer without going to another machine and downloading them and putting them on some way, either burning them to a CD or putting them on a USB key and plugging into that computer. Once you get a computer then on the network, you can download all the rest of the drivers you need for video and everything else on that computer. So here they're saying that operating systems have a lot of the drivers built in. If they're not available, then you have to install and download and install them, and you can usually get the updated ones from the manufacturer's website. So once you've got the network card installed and the drivers are loaded, you can verify functionality. There are several ways to verify functionality you should be aware of. In reality and in practice, what you do now, because almost everyone's on the internet, once you've put in a new network card and you think you've configured everything right, try to open a web page. If you're able to get to google.com or CNN or anything like that, then you know your network card is communicating because you were able to get out on the internet and pull up a site. If not, though, you can use what is called a loopback plug. And you can make one of these or you can buy one of these. And what you do if you make one is that you take the wires and you take the transmit wires and the receive wires and you loop them back into themselves on the little connector. We talked about RJ45. That's a little connector that goes into the wall. Well, a loop back, you literally just loop those wires back into it so that what the card transmits, it receives. And that way you can test transmit and receive on a computer by letting it talk to itself. One thing I always do if I think a network's not working, look at the link light, what's called the link light. Almost all network cards have got little lights on them. If I go back to the diagram here of the built-in one, for example, if you look at the top of each of those, there's two little lights on each of those network cards. And one is a link light. And what a link light does is that light is solid if the device is connected to a switch or a hub. If it's got a connection to anything else, that light will be solid. Then the other light is a transmit or receive light. It'll blink as data is coming in or going out of the network.
Which one is that?
It's these two devices. And it's different on every computer, but usually the light on the left is the link light. I don't know why that is. I don't know if there's a reason behind it. It just happens to run that way a lot of the time. You can also look for the link light on the switch, because not only will that light be lit up, but then whatever port that wire's run into on the switch, the light will be lit up. And some hubs and switches have actually lights under each port number. These back here, the number itself is the light. So I know if I plug a device in, I can look back there. If I know it's port 18, I'll look at port 18 on the switch. And if the number 18 is lit up, then I know that that's live. That can help you eliminate problems like with cable, because if it's not working, you're not able to get out, but your link lights are lit up, then you know to kind of look at software, because you know the cable's good, at least, or it should be good. It's good enough that it's making a connection. Okay, and then use some of the simple commands. I've showed you ping before. Once you've connected, try to ping something. Ping an address out on the internet and ping something locally. Remember, you should always get a response from pinging what? Right, 127.0.0.1 should always respond. So that's a good test. Ping that address and see if you get anything back. If you don't, you know you got a software problem. Okay, so some interfaces, and this is more with actually switches than with network cards and computers, have what are called GBICs and are modular interfaces. And what that means is that's an interface that you can change on a switch without turning the switch on and off. And even though they're faster now, like you can get 10 gigabit GBICs, they're still just called GBICs because the term has been around. And usually what a GBIC is on a switch is a special port that can be different media from everything else. Like on those back there, I don't know if they've got a GBIC port or not, but if they do, the GBIC could be fiber. So we could have copper run in the room, but I could put a GBIC in that's fiber so that I ran fiber down to the first floor or wherever my next wiring closet is. And on some devices, they're called SFPs. SFP is just a small version of a GBIC. And based on who you're talking to and what company made the device, you know, will be what they'll call it. So here they're showing an example of an SFP and a GBIC. And the GBIC here, you know, has just got a connection for RJ45, which, I mean, you see some of those, but not often. Usually now that's going to be for fiber. In the old days, the GBIC was important because that was the fastest port on the switch. Maybe all the other ports were 100 megabit, but the GBIC was the 1 gigabit port. So if you had a local network that wasn't connected to the internet, you might put your server on that GBIC port because it'd be faster than everything else. If it were connected to the internet, you would put your backbone link in there so that it would be faster than all the other connections. And then you see the SFP is the same thing, except it's just smaller. And that's a fiber connector. See, there's the where you would put the transmit and the receive fibers. All right, so a repeater operates in the physical layer of the OSI, and it has no way to interpret data. All a repeater does is repeats a signal. It just reads it in and ups the signal and sends it back out. A hub is simply a repeater with more than one port. They typically have lots of ports on them, and most contain an uplink port. And the uplink port is the one port you would connect to another switch or hub to have more than one together, so that if you needed to have more than that number of computers in a room, you could put more because you could add more hubs. Hubs generally are not going to be seen in modern networks. It's important that you know about them, though, for legacy purposes in case you go in to update an old network somewhere, because those old hubs are something you're going to have to deal with on that network.
So most of them go with switches and routers?
Mostly switches have completely replaced hubs. The reason hubs were popular is because memory used to be very expensive, and switches need memory, hubs don't. So your cost per port on a hub used to be lower than it would be on a switch. Nowadays, it's actually almost kind of reversed. It's hard to actually even buy a hub because no one uses them for anything. If you go over to Best Buy, you know, you can find switches everywhere. I bet you can't find a hub anywhere in that store. And that's because memory's cheap now, and these little hubs, you know, little switches are easy to operate. So a bridge is a device that connects two network segments. And a bridge analyzes the frames and determines where to direct them. It operates at the data link layer of the OSI. So if I say data link layer, what number layer is that? Layer 2, right. A switch or a bridge is a layer 2 device. A bridge has a single input and output port. It's protocol independent, and it creates a filtering database, and that's a MAC table. We're going to learn more about MAC tables later. So here they're showing a bridge, and basically what a bridge does, you've got two hubs, you've got that bridge in the middle. So if computer 1 wants to communicate with computer 2, the data is seen by the bridge, but the bridge doesn't pass that data through. The bridge blocks it. If computer 1 wants to talk to computer 4, however, the bridge passes that traffic through. So what does a bridge kind of sound like to y'all? A bridge is basically a one-port switch. That's exactly what it is. These were first because, again, memory was expensive, so switches were expensive. We would put a bridge in to break up a network. Like in the old days, labs like this, say these 3 labs that are right here together, each lab would probably have its own hubs, and then there might be bridges between the labs if they were all connected together and not on the internet. And then these computers would be kind of independent unless they needed to talk to the computers in the other room.
So you're saying that,
Do what now?
so you're basically saying, I was on the one computer, I could talk to 4, 5, and 6, but I couldn't communicate with 2 and 3.
No, you could communicate with any of them, but the traffic would, if computer 1 and computer 2 wanted to talk to each other, the traffic of them communicating would not be seen on the network by 4, 5, or 6, because there would be no reason for that traffic to move on through. Come on in. No, come on in. The traffic would be blocked, so it wouldn't go on through. And that leads us to a switch, which a switch subdivides a network into what are called segments. Traditional switches operate at the data link layer of the OSI model. And that's important because we're talking about a layer 2 switch. But I want y'all to be aware of that modern switches, like those back there that are managed, also operate at layer 3, possibly 4. And you can purchase a 7-layer switch now, which means that the switch is able to not only look at the data, but it's able to read it and determine what it is and make decisions on whether to pass it on or not. In the old days, those switches were always layer 2 devices because a switch only worked with a MAC address. Remember the big difference in 2 and 3. Layer 2 is a MAC address. Layer 3 is what? Layer 3, we're working on an IP address, exactly. So switches interpret MAC address information. And most of them, they have their own little operating system. They have memory. They have a small processor that determines where to actually send data, and then ports.
Is that kind of like that little Google thing you have on your television that switches off when you go to it?
No, a switch is that you remember back here on the wall when I showed y'all that? That's a switch. So installing a switch is pretty easy. Generally, find out what wire, make sure that the wire you've got is proper. Verify the switch placement, turn it on, make sure the lights work. If it's a layer 2 switch, there won't be very much configuring to it. You're just going to turn it on. If it's layer 3, you'll need to configure it. You'll need to give it an IP address and tell it what you want it to do. Connect a NIC to a switch port. You plug your wire in, your wire should light up. And then if you need to connect it to a larger network, plug it into the larger network. So here they're showing an example of a typical switch. And what a switch does, remember, is it creates separate collision domains. So where we talked about a hub, remember, being a problem that if 2 computers tried to talk at the same time, a collision would occur. With a switch, collisions do still happen, but they're way, way, way less frequent. Because what happens is when your computer wants to talk to another computer, the MAC address goes out, on the network, the request to whatever the destination MAC is. That switch has a table that says this MAC belongs to this port. So it only sends the data out the port it was designed for. That means in this case, if that laptop wanted to print to that printer, the workstation and the server aren't even going to see the traffic. They don't care about it. They don't need to know about it. So it's just the laptop makes a virtual connection to the printer. So differences in switches may involve the way that they're going to interpret the frames, and then what's called a frame forwarding decision making. And what that means is there are different ways that switches decide how to read the packet and determine how to push it through. Now, because a switch has to actually read the packet versus a hub, there's a little bit of latency there because the switch has got to decide what to do with it. And even though there are 4 switching modes, the 2 that are most common are cutthroat and store and forward. And in cutthroat, the header is read, and as soon as the first 14 bytes of the packet are read, the decision is made where to send the packet. So it's quicker because it doesn't look at the rest of the data. It only reads the first 14 bytes of it and then makes its decision on where to send it. The problem with cutthroat is that an error, if there's an error in the packet, the error is sent on through because the switch is not reading anything but that MAC address. If it can't read the MAC address because the whole packet's garbled, it'll be knocked out. But if it can read the MAC address and the data's garbled, the packet gets sent through anyways. And what happens, sometimes on a network you get a packet that's too small because the data didn't get put in the packet. And these get sent on. These are called runts. So again, cutthroat cannot determine what the problem is with a packet. But the advantage of that is speed. It's going to work a lot faster than the other method. This is good for small work groups with not a huge number of devices. And let me explain, when they say a large number, they mean a pretty big number. Cutthroat would work fine in this lab, even though we've got 30 computers in here. So store and forward reads the entire packet and puts it in memory. And it also checks the packet for accuracy. So what store and forward does is reads an entire packet off the network and checks the CRC field in the packet to make sure it's right before it sends it on. Now, y'all remember we talked about a CRC field and how that's a little mathematical formula that a computer runs to determine if data has been sent right. Well, a switch actually checks that before it sends it on. It's slower than cutthroat, though. But it's good for larger environments and mixed environments. One thing about store and forward is it can handle network segments that are at different speeds. All of your switches at home that are multi-switching, where they will run 10, 100, and a mixture of the two on the ports, they're store and forward because they've got to read that whole packet and then they send it out the other port at a different speed. So then we have what are called VLANs, and VLANs is a way to logically separate networks within networks. VLANs allow you to create a network that maybe acts like one logical local network, but is in different rooms. Like we could create a VLAN, for example, and put the first row of computers in here in a network with the first row of the computers in 203. And then, even though they're physically in different places, logically to the network, they would look like one network. They'd have one set of IP addresses. They'd have one broadcast domain. So a broadcast domain is a port combination making a layer 2 segment. Ports rely on layer 2 to forward broadcast frames. A broadcast frame is just a packet on the network that has a special purpose, but the MAC address is all Fs all the way across. And that means that it is sent to all ports on a switch. Everything is sent to all ports on a hub, but a broadcast is sent to all ports on a switch. A broadcast domain is only separated by a network device like a router because it breaks up the broadcast. So a collision domain are all the ports in the same broadcast domain. So here they're showing that I've got VLANs. And what these VLANs are going to do for me, you see that a couple of the computers in the VLAN are on the second switch, but logically they're going to act like they're with that first switch in that first network. Those two switches are connected together, and they're connected to a couple of other switches. The nice thing about VLANs is they don't care how far the things are geographically located. Some businesses will do this for security, like let's say you're a bank, and you're in a high-rise downtown. Maybe you want to VLAN all the people that deal with loans together, but physically maybe some of them are on the second floor and some of them are on the 80th floor. So a VLAN makes it where you can put them where they look like one network even though they're spread out all over the building. That's the big purpose of a VLAN, is for that. So VLANs are flexible. You can use ports from multiple switches or segments. Reasons for VLANs are to separate user groups, to isolate connections. You can use priority device groups. That means you can make if you've got VoIP on your network, you can make a VLAN and put all of your VoIP phones in it, and you can give that priority on the network over the other stuff. They also can group what are called legacy protocol devices. That means if you've got some devices that are running an old insecure protocol you need for some reason, but you want to isolate from everybody else on your network, you can do that. And they separate large networks into smaller subnets. So switches typically have one default VLAN, and the default VLAN can't be deleted or renamed. And the reason for that is if you turn on VLAN on a switch, everyone has to be a member of some VLAN to be able to communicate. So it makes them all a member of that default VLAN. Then you determine what VLANs you want to put them in later. You would do all of this on the switch itself, right? Based on who made the switch, if it's Cisco, it would be command line stuff you type in. But some of these switches, like that HP one back there, have a web page interface. You go to that web interface and you'll see a picture of each port, and next to it will be like a field for a VLAN number, and you put the number of the VLAN. And because of the way that VLAN works with IP4, you can only have 255 of them on your network in total. So you have to, decide how many VLANs you need, and you break everything up and put it into those VLANs. Maintaining VLAN is done with the switch. So a problem with VLANs is that you have potentially cut off a group from the rest of the network. Because you've made it a separate broadcast domain, now it has no connectivity. So the way that you have to connect that to other networks with VLANs is with a router. And the reason, this is where the lines get kind of clear, kind of blurry. A layer 3 switch can also act as a router for VLANs. It's doing a routing function even though it's a switch. So I know that makes it kind of, these devices are not black and white anymore, and that makes it kind of hard to grasp this when you first hear it, because I can't say, well, this device does this, because some of these other devices do other things as well, You might think this is a router, but it could be a layer 3 switch that's acting as a router. So you also have to, on a VLAN, have what is called a trunk port. VLAN for security means that if a port is not in that VLAN, is not a member of that VLAN, that port will not see the traffic that's in that VLAN. So you have to have a trunk port in order to connect that switch to other switches. If all of your VLANs are on one switch and it's an isolated network, you don't need a trunk port. But if you're going to connect it, like in our example here where I said this first row to 203, that switch and the switch down there, there's got to be a trunk port on them so that that data from the different VLANs will travel through it. And VLAN adds a frame that contains a VLAN identifier in the header on the packet that's sent out on the network. So that packet's going to have a VLAN frame header in front of all of the other data that we've talked about that it would be in it. So here is an example, and you see they're showing the trunk port is the wire that runs between the two. And then I've got separate VLANs in each of my devices. And here you'll also notice that some ports are in more than one VLAN. So something that we have to have if we have multiple wires connecting switches to other switches, which is a good idea for backup, you know, things happen to wires, is called spanning tree protocol. And this is defined by IEEE 8021D. And what spanning tree does is it prevents what's called a traffic loop or a broadcast storm. And basically, I'm going to draw it out because it's easier if I draw it for you to understand it. If I've got a switch here and a switch here, and I've got some computers off of each of them, sometimes maybe I want to make sure that the two are connected even if something happens to the wire. Or I want to load balance because there's more traffic that needs to go between them. So I will put two wires running from one switch to the other switch. Okay, if this computer wants to communicate with someone and it sends a request out for a MAC, a MAC address, whatever the MAC is, this switch looks at it and says, I don't know who this MAC address belongs to, so I'm going to send a broadcast request to find out. So it'll send a broadcast request. This switch gets it and says, I don't know who this is either. I'll send a broadcast address. So it'll go back. This loop will be created, and it will eat up all the available bandwidth because the two routers without spanning tree don't understand that each of them are responding to the same thing. So it'll just go on and on and on your network. And a broadcast storm will bring a network completely down because there's no room left for traffic. It's all being spent on broadcasting. So with spanning tree turned on, what it does is it actually looks and reads those packets, and if it sees the same thing over and over, it blocks it. So it prevents that broadcast storm from ever starting. And the way that it works, you have to select a root bridge. So one of your devices is going to be the root bridge, and it will determine what the best path to the other network is. So here they're showing their example of a spanning tree, and theirs is a little more complex than I made, the one that I showed you. But you see how they've got multiple wires. The reason for that is, let's say the wire between switch D and E broke. This network would stay up because there's still a path for everybody to communicate. If the wire between B and E broke and D and E, they could still communicate because everything could go from A to D to F and down. So it's just a way to add backup to your network in case something happens with wires. Here's their example in that same one. They're showing that certain ports are blocked by the root bridge until they're needed. All right, so spanning tree was originally introduced in the 80s, but the original spanning tree protocol was slow. So it has been updated to the rapid spanning tree, the 802.1W standard. Now, different network companies, specifically Cisco, and you're going to hear this a lot, Cisco has their own proprietary versions of these protocols. And Cisco's stuff generally works better, but the trade-off is to use Cisco's proprietary spanning tree, every device on your network's got to be a Cisco device. If you're using the Extreme Networks version or the Juniper version, the same thing. Everything on your network's got to be the same device. It is actually pretty difficult to do some of the upper level switching stuff with devices that are made from different companies. That's why you tend to see in a network, you'll hear the admin say, I'm a Cisco shop, or I'm an HP shop, or an Extreme Network shop. What that means is he's decided on that product and he's going to buy that product. For compatibility with everything else, he's going to stick to it. If you go with Cisco on your network, stick with Cisco. It's going to make it easier on you. And with some of the new spanning tree, it's already turned on automatically in the switch, so you don't have to do any configuration. Okay, so layer 3, we talked about, that's a switch that can read IP addresses. Those switches can make decisions not just on MAC addresses, but based on IP address. Layer 4 switches can look at layer 4. And then content switches, which are a relatively new thing, can actually look all the way up to the application layer. And some of those can do things like advanced filtering. They can keep statistics on things, and they have some extra security. Maybe, for example, I don't want to allow anybody to do web traffic between 12 and 1 on my network. Well, with some of these upper layer switches, I don't need a firewall to do that. I can do it on the switch. I can just say, do not pass port 80 traffic during these times.
So it acts like a firewall as well.
See, that's where these lines get gray. Some of these devices can act as all of these different things together. So distinguishing between 3 and 4 is sort of a manufacturer issue. Higher layer switches cost more than layer 2 switches, and they're used in backbones. Most large companies now are just buying managed switches. For home, though, there's no need for it. I mean, you know, the little $10 switch you get at Best Buy is fine for you at home. It's just in a business, if you want to be able to do some of these higher level functions like backup connections and things, you need a layer 3 or better. So a router is a multi-port connectivity device. It directs data between network nodes, and it integrates a LAN and a WAN. So it's a connection between a local area and a wide area. Routers operate at layer 3. That means that they use what? Exactly. They're using IP addresses. They use LOT, which is logical addressing. They're protocol dependent. Routers are slower than switches and bridges, though, because they've got to read the layer 3 data. So not only do they have to read the MAC address out of the packet, they got to look further into it and read the IP address out of the packet. Routers are being replaced by layer 3 routing switches in traditional standalone networks. And that means like in here where we got VLANs. VLANs are turned on this network because when we switch it to the cyber network, we can isolate this room from the other networks in the building. And the reason it was all designed that way originally was for like the defense classes. Let's say that I wanted to release a virus in this room to let y'all see how a virus actually transmits around on a computer. Well, BIPSI doesn't want a virus getting out into all the rest of the machines. So by making a separate VLAN that we can turn off or isolate, we can kind of separate this network from anything else. But because it's a separate VLAN, in order for it to be able to communicate with any other computer on this campus or the internet, that switch back there has got to route the traffic from this VLAN onto the campus VLAN. So in that case, that switch back there is acting like a router. So routers have intelligence. They track node locations and determine the shortest, fastest path between nodes. On large LANs and WANs, routers are absolutely necessary. Routers have an internal processor, an operating system, memory, input-output jacks, and management control interfaces. Routers are basically little computers if you really think about it. If we boot up those Cisco's over there and you see the boot up, they boot up a lot like Linux. They go through and they do a power-on self-test, and then they load the operating system, and then they turn on the ports, and then they turn on security. So, do what now? So, multi-protocol routers can have multiple network interfaces on them, and they can handle multiple slots. Inexpensive routers are good for small home and office use. Most of you probably have a router at home, whether you know it or not. If you've got a wireless access point and you got more than one computer on your network at home, you've got a router. They're not separate devices anymore. That's the key to remember. Like, I've seen these devices at Best Buy now for cable modem users. That's the cable modem, the firewall, the wireless access point, and a 4-port hub all in one device. Even though it's actually 4 separate devices, they're all put in one case. They're all built together. There's pros and cons. I mean, it's a single point of failure, but then for a home user, it's easier to manage because it's one device to deal with. So here's some examples of some routers. They've got a little, routers, yeah. That's a little Netgear wireless router for home that's got a switch built into it. The one in the middle, I can't read it. It looks like maybe that's an Extreme Networks, or Juniper, one of the two. Is it Juniper? It's got several ports on it. It's got some switch functions built into it. And then over on the side, we've got a big router. That would be like a core router. And you would use something like that to route, thousands of computers. So something like that would be what you would find downstairs for the campus that would route the entire campus out onto the internet. So routers can connect dissimilar networks. They read layer 3 addressing. They determine the best path and they reroute traffic. The fact that they can connect dissimilar networks is important because a router can since it's working at layer 3, you can put an interface in it. You can have token ring on one side and Ethernet on the other side. And the router can deal with that. Do what? Right, exactly. All right, so some routers can filter broadcast transmissions. They can enable segregation and security. They support simultaneous connectivity. If you buy some of the larger ones, they have fault tolerance. They can monitor the traffic, and they can diagnose and trigger alarms based off the type of traffic they see. Where you place a router determines what type of router it would be called. An interior router directs data between nodes on a LAN. An exterior router directs data between nodes external to a LAN. A border router connects an autonomous LAN with a wide area network. And then routing tables are what identify which routes the router itself serves. So our little router back here that's putting this VLAN onto another one, that is an interior router because it's all one local area network. But then downstairs, we've got the big router, a border router, that's connecting us out to the wide area network of the internet. Well, no, a router doesn't do any, laptop doesn't do any routing. Because a laptop, is just connected to a network. An exterior router would be like a VPN, a virtual private network, or something along those lines. Technically, you could call the routers that route the buildings here exterior routers because it's separate IP addresses, so it's separate networks they're connecting. But in actual practice, I would probably call all the routers here an interior router except the big one, and it would be the border router that routes us out on the network. So routing happens in two ways. It's either static or dynamic. In static routing, the router is configured to use specific paths between the nodes. Static routing, you assign the routing table to the machine. You go in and tell it what the routing table is. In dynamic, it automatically calculates the best path. So installation for the small home and office ones, they're usually web-based. You just go on and tell it a few little things to set it up. But then for some of these large routers, there's a very complex number of steps you have to go through to set it up. And the reason for that is not to make it harder on purpose, but those routers will do nothing more than what you tell them to do. And that is for security. That router is only going to do what it's told, so you have to go in and tell it every single thing you want it to do. Here they're showing an example of a larger network. We've got a couple of interior routers and then a border router connecting us to the internet. And then those switches are connected to routers. So here's a question to make sure y'all understand it. Those are switches, so how many collision domains are there? Two. All right, no. A collision domain, remember, with a switch, every single port is a separate collision domain. Oh. So each of those computers, I'm not going to count them up, but each computer is its own collision domain. How many broadcast domains are there? Y'all got that right, too. Because the routers are going to break up the broadcast domains.
The switches just give you additional ports.
Switches give you ports, but unlike a hub, a switch doesn't pass all the traffic to every port. It just sends it to the one it needs to go to. That's why you use a switch over a hub. All right, so routing, you've got to determine the best way to route, and that's dependent on hops between the nodes, network activity, if the link's available, the speed, and the topology. And all of this varies greatly based on what router protocol you're going to use. So routers use what are called metrics to determine how to route data. And some of the different metrics that can be used are the number of hops. Do y'all all understand what a hop is? All right, a hop is actually just a connection from one router to another. Like if I run a trace route, each of these numbers are a hop. And what that hop is that is a different device that is routing my data out onto the internet. So see there, the first hop is the wireless access point in the back because my computer's wireless. The second one is the gateway for BIPSI. The third is our connection on Delaney, which is what our big network is connected to.
So it kind of goes in order.
Right, that's where it's going out on the network, exactly. 4 and 5, only because I know, from working as a net admin around universities what that is. That's actually a connection over at the medical center. Because our connection to Lonnie goes to the medical center, and then there's actually a piece of fiber that runs down I-49 that connects this part of the network to LSU, which is where our internet goes out. So hop number 6 there is probably actually a connection in Baton Rouge. And these others, I don't know what they are. I use the command traceroute, T-R-A-C-E-R-T. And you can traceroute any address. I just used 8.8.8.8 because I know that's Google's DNS server. It's just a common one that I know that I test stuff with.
I guess when you're as it's running, it's kind of amazing when you sit there and think about it that usually if you were going to it, you would just take Google and load up.
Right. But this is what it actually went through.
All the different little pit stops, more or less, you might say, it's making as it's going.
Exactly. And see, number 12 timed out. Number 12 is probably a firewall. Google probably has a firewall before you get to their DNS server. And that firewall is not going to respond to anything, but it's going to let traffic through. So see, we're 13 hops away from Google's DNS server. But he brings up a very good point. If you connect to it, it's almost instantaneous. You don't realize all of this is going on. So because routers are going to have different information at different times when there's an outage, a process called convergence has to take place. And that is the amount of time it takes a router to realize that other connections have gone down. Like if I were to draw a big network up here on the board and show it to y'all, and then one piece of it were to go down, it would take a little bit of time before all of the other routers learned that one connection went down. Lots of places will have a backup connection, but usually the backup connection's slower than the main connection because it's cheaper. Like over at LSUS, we got our connection to Lonnie that connects us to the network, but then we had a backup DSL connection with Bell South. Now the DSL connection was terribly slow, and the whole campus, would almost grind to a halt on it, but it still gave us some connectivity. So do what now? DSL is like a home DSL modem, not dial-up, but slower than what we got. So when that happened, if the router went down and we had to switch to that, it took an amount of time before the other routers out on the internet knew that our IP address had changed and that our connection had changed and was using this connection. So the time in that is called convergence. And it varies. It's from 30 minutes to a few hours to a couple of days with some really, really, really large networks. Because if you've got a network with, tens of thousands of routers on it, it's going to take a while for everybody to realize what has happened. So some of the routing protocols, distance vector protocols determine the best route based on distance. Distance is the hops, latency, or network traffic conditions. And an older one that's easy to understand is RIP. And RIP only looks at hops between connections. But RIP has a limit of 15 hops. RIP is a type of what's called an interior gateway protocol. It's good to use inside of a local small network. It is slower and less secure than some of the other protocols, though. RIP2, pardon me, is the new version of RIP. It generates less broadcast traffic, so it's a little more secure, but it still cannot exceed 15 hops. BGP is a common one. It's called Border Gateway Protocol. And it communicates using what are called BGP messages. There are several factors that determine the best path with BGP. And you configure it to follow certain policies. So you go in and configure BGP to do what you want it to do. BGP is an EGP, though. It's an exterior gateway protocol. And it is a more complex protocol, but it's what's used on the internet. Link state protocols are how routers share information. And each router independently maps the network determined on the best path. And one of those that you'll hear is OSPF. And again, we're getting tied down in acronyms here. I don't know how much of the routing stuff you're actually going to see on the test. Have y'all, from the exam crams, have y'all seen a lot of these? Or?
Yeah.
OSPF, yeah. Mm-hmm. So it's open shortest path first. It has no hop limit. It uses a complex algorithm to determine the best path. But each router has to maintain a database containing the other router's links. Another one is called IS, or intermediate system to intermediate system. This one's for interior routers only, and it supports 2 layer 3 protocols. It's less common than OSPF, but it's an open source version. Then some use what are called hybrid. And here again we get into network specific things. eGRIP is a very popular protocol, enhanced interior gateway protocol, but it's Cisco proprietary, so only Cisco networks can use eGRIP. eGRIP has a very fast convergence time. This is one of the things that kind of made Cisco what it is today. They support multiple protocols, and it's less CPU intensive than OSPF, so it's faster than OSPF, but if you're going to run it, all your devices have got to be Cisco, because they've all got to be able to talk eGRIP. So this is a good little table, and I would take some time and kind of memorize this table. Make sure you know the types of protocols and their locations. You might get a question on the exam that says something like, of these 4 protocols, which 3 are distance vector? So make sure you kind of know that part. Right, in this case that would be the answer, RIP, RIP2, and BGP. So a gateway is a combination of network hardware and software that connects 2 systems using different protocols or architecture. A gateway repackages information. It usually resides on a server. Popular gateways: an email gateway, an internet gateway, a LAN gateway, and a firewall is a type of gateway. So that is a quick rundown on Chapter 6. Do y'all have any questions? In this one, I'm going to let y'all make cables, but that's going to be about the extent of it. Simply because we've got to get through all of this theory for y'all to take the test. I mean, I could let y'all take one of these computers apart and put a network card in it, But I do want to let y'all try to make a cable. I'm going to let y'all do that one day just for experience. I think it's difficult to make cables. I think I've told y'all that before, though. I'm colorblind, so the orange and the brown one are kind of rough for me. But mainly for this class, the big thing is getting y'all the stuff to take the certification exam. The Net Plus, y'all are going to take it. I'll have to get the exact date. It's going to be right after finals start. So, yes, you have to take it after this class. Yeah, it'll be in December. It's not hard, but there's a lot on it. There's a lot of stuff you're going to have to read for it. So, okay, I finished chapter 6. So to get us back on schedule so that we're where we want to be, I'm going to do 7, 8, and 9 for sure for y'all to watch online, and maybe 10. So, you know, I'm going to be gone for that conference. I won't be here this weekend. We're all out next week for break, so y'all won't see me for 2 weeks. Get on Blackboard. Just kind of keep an eye on it. I'll put those up. I don't really care when you watch them, but make sure you watch 7, 8, and 9, or 7, 8, 9, and 10 before we have class again. I'm also going to go ahead and do the rest of the chapter quizzes, so those will be there for you. Yeah, just do them whenever. Don't wait, though, because the further we get into this stuff, the more you're going to forget the stuff that was on the first one. So make sure y'all get started on those right away. I would, if I were you, I'd watch the YouTube video for that chapter right before you do it, and then do it. Do it while it's real fresh on your mind. You know, those videos are up there. I've still got to put up last week's, but it just finished, you know, transcoding, so I'm going to do that today. That way, you know, y'all will be able to kind of get back to, it'll hopefully jog your memory. And the videos are just basically my screen. They're this screen and me talking, so you'll have to filter some of it out, but I think it'll maybe be a good little practice for y'all. Don't forget about your exam cram either now. That should be helping you prepare for this test. That's the Cram Master stuff you're supposed to be doing. And, you know, by the end of the class, I'm going to want 60 questions in each section. Really try to focus on that during the break if you can. I mean, I know y'all have got other classes to deal with, but the more you can spend on that, the chances are higher of you passing this test. No. You'll get different questions each time. But if you have any that you have a question on, print it and bring it to me. I'd be glad to discuss any of them in class.
Well, that's the test you're going to give us, 60 questions?
No, just say, when you go to exam frame, now has the 5 with the same.
Do 60 in each of those 5 sections. And that's not your chapter quizzes, though. That's a separate grade. But that is the product you really need to spend the most time in if you want to pass the cert. I know I hate saying that to y'all, but it really is relative. The more time you can put into it, the better you're going to do on it. Right, yeah. The more you can put into that, the better. And as y'all are doing that, if y'all have one you don't understand, print it. Print the whole question and bring it to me. You can't just tell me numbers because I won't know what question number you got. But if you'll screenshot your screen and screenshot it with the answer that's right and the answer you picked, I'll try to explain to you why the answer you picked was wrong and why their answer is right. So that, you know, I'd rather do that than anything else, than even these lectures. So at the first of class, if y'all have questions on some of those, bring them to me, and we'll spend class time going over that, because that's the stuff you're really going to need to learn for the cert. Good, good. All right, well, y'all have a good break. I won't see y'all again until after Thanksgiving, so...
You must go down the same trip, right?
All right.